Okay, so where did we leave off? We left off with the definition, right? We talked about the definition, and we were talking about how you can improve the completeness and soundness errors in these cases by repeating and taking the majority in general. Though we didn't really look at the proof of that. Um, so we saw the proof of how the amplification of soundness when you start with perfectly complete. You start with the perfectly complete proof. You just repeat and make sure you ask for all the iterations to accept, and we saw how it amplifies. More generally, as we were discussing briefly earlier, if you don't have perfect completeness, if you only have like some 2/3 and 1/3, let's say, or really any gap is good enough. Even if you have like something like this is 1/4 and this is 1/5, even that's good enough. You just have to repeat the protocol many times and place the threshold at the right point. You have to say, okay, if this succeeds, if here you have greater than 1/4 and you have less than 1/5, then you will ask something like, I repeated t times, and the number of iterations that pass has to be larger than like the middle point, whatever the arithmetic mean of 1/4 and 1/5 is. So it has to be more than that, right? And if it's less than that, I will reject. So that's how you will amplify this. And the proof in that case, it can be done in a very similar manner. Essentially, these ideas are sufficient to complete the proof. Yes, maybe you have to be a little bit more careful, but you can pretty much do it. You can pretty much do the proof in this way. And okay, there's actually one part that we did not talk about. That's a bit more that you need to know to complete the proof. But I'm not going to go into that. And in general, actually, I wanted to say this. If you want references for any of this, there are a few resources. So if you go to my website, I taught a course on probabilistic proof systems a couple of years ago. And the course webpage will be linked to from my webpage. So that will have lecture notes on all these topics, and it will have other references to textbooks and other courses on this topic also. So if you're interested to know more about any of these things, you can look into that. And if you don't find resources on some topic there, you can email me, and I'll find something for you. Right. So yeah, so there I have the proof for the more general case is in one of the lecture notes. So you take a look at that if you're interested in understanding how it works. Another thing I want to say here is, okay, so we saw this one approach to amplifying this, right, where you take the protocol and you repeat it several times, one after the other. You can actually do something a bit better than this. Instead of repeating this protocol sequentially t times, you can actually repeat it in parallel. Right? And this makes a difference because it's an interactive protocol. It could have multiple messages that are being sent between the verifier and the prover. But what you can do, what I mean when I say you can do it in parallel is, I mean you start at the beginning and you have the verifier, right? You have one verifier that's coming from, that has this guarantee with like 1/3 or whatever. And what you will do is you will make it, just run it several times independently to generate the first message of the protocol t times. And you send all of it together to the prover, right? And then the prover is supposed to respond to each of those messages together. Like it's supposed to, it'll compute the response to each message and take all of them and send it to you as one big message, right? And you can keep doing this. And this also works to amplify the completeness and soundness of the protocol. Here also, if you start with some gap between let's say 2/3 and 1/3 or some gap between these, you can get to 1 minus little of 1 and little of 1. That works, but it's much harder to prove that it works, because the correlations that we have to deal with here, right? Here we said that these things you cannot treat them as being independent, so you have to very carefully deal with these correlations. They become much worse in the other case, because here we were at least able to separate out the iterations of the protocol, and we only had to deal with correlations between entire iterations. We were able to define these events, and we only had to deal with correlations between these events. But if you're doing things in parallel, there could be correlations between different messages of the protocol. Like imagine you're doing 2 iterations in parallel, right? The prover may decide to respond to your second message in the second iteration based on what your first message in the first iteration was. So the correlations can be much more complicated, much more complex in the sense, and much harder to deal with. But we can deal with them. So and there should also be a reference in the notes to how you prove that parallel repetition works to amplify things in this case. But in general, you have to be more careful, more wary of these kinds of correlations. Right. So this lets us this the fact that you can do this amplification lets us just define, gives us much more leeway in how we define this large and the small here, right? So unless I specify otherwise, I will generally use 2/3 over here and 1/3 over here. This will be my definition of completeness and soundness, because you can just amplify them anyway, so it doesn't matter that much. Okay, so what have we said so far? Just to recap very quickly from the beginning, we started by talking about proofs and how you prove things in mathematics, where you have these kinds of non-interactive proofs where you can write down the proof and the proof sort of always works, right? You can just verify this proof non-interactively and you can prove these things. And then we saw this other way of doing proofs, which I want to point out is letting you do some things that we did not really know how to do with these non-interactive proofs, like with the example with the graph non-isomorphism, right? Here we have a very simple, very efficient protocol, a very efficient proof in this model, in the interactive proof model, whereas with the non-interactive proofs, I have no idea how to do this. Like the best proofs I can come up with for proving that two graphs are not isomorphic is I don't even know how to do it in a polynomial amount of time. Like if I want to write down the proof, I don't know how to do it with polynomial of in n number of bits, right? So, but whereas this is like a very small number of bits of communication, very efficient verification. So this is already showing us that these kinds of proof systems can be more powerful. It comes at a cost, right? The cost is that here there are errors, whereas with these mathematical proofs there are no errors. Like if you see the proof, then it's just it either completely convinces you of the statement or it does not. Whereas here you don't really have that. Right? And there are also certain other things that are not really modeled by this particular modeling of interactive proofs. For example, this doesn't really capture things like Bayesian priors. So if you think about things in the real world, for example, right? Like if I told you right now, for example, that it is raining outside, you are more likely to believe me than if I told you it is snowing outside, right? Not because it's impossible that it will snow here. Maybe there's like a very, very small chance that the weather gets so bad that it starts snowing in Madras, right? But it's much less likely. Like your prior belief, the prior probability you assign to this event is much lower. So the standard of proof that you will expect for a statement like that should be much higher, right? This is this Bayesian way of thinking about the world and maintaining these priors on the world. But that is not really captured over here. We don't really deal with that at all. Instead, here we are dealing with some kind of worst case events where we say that for every, when we ask about this instance wise guarantees, where we sort of treat every statement equally in some sense, where for every statement I want like the same amount of probability of success and so on, right? So that's not really captured by this abstraction. But this has proven to be very useful. So even without capturing things like that, this has proven very beneficial, because a lot of the time when you're dealing with these computational problems, our beliefs sort of are not that strong. It's not really clear how to assign these Bayesian priors anyway, so it doesn't really matter. Yes, so but the way I got here, I was talking about the fact that these proofs have errors, whereas mathematical proofs do not, right? So these are two ways in which they are different so far. That these proofs are interactive, mathematical proofs are not interactive. Mathematical proofs don't have errors, these have errors. And there's another one important way in which these are different from typical mathematical proofs, which is that these proofs involve randomness. Right, and here you can see this randomness is, we're using a lot of randomness here, and this randomness is quite crucial, because if the prover knew, for example, if the verifier here had been deterministic, let's say it always picked b to be equal to 0, then the prover can very trivially make the verifier accept here, right? You can always send b prime equals 0. So in this protocol, the randomness is very crucial. The fact that there is randomness involved in the verifier's algorithm is very important. And further, this is not just for this protocol. More generally, for any interactive proof really, for it to be any different from non-interactive proof, this randomness is crucial. It needs to involve randomness. Yes? It really depends. If you're dealing with yeah, so you have to be careful what you're using it for. And what kind of pseudo-randomness we mean. So it depends more on the protocol than it's hard to make a more general statement, especially with the proof being computationally unbounded. It's hard to say something general. Yeah, I want to say that for these interactive proofs to give you any advantage at all over non-interactive proofs, which is these mathematical proofs, they need to involve randomness. So why is that? Why am I saying this? Exactly, right. If the verifier was not randomized, then the prover can just run the verifier's algorithm itself, because the only thing here that the prover does not know about the verifier is its randomness, right? The prover does not know what this bit B is, and that's where the power of the proof is coming from. But if there was no randomness on that side, the prover can say, okay, this is what the verifier is going to do anyway, and they can write out the entire protocol and send just the protocol, that entire transcript to the verifier. The verifier can look at it and say, yeah, this is what I would have sent anyway, and I accept this as a proof. Right. So for this reason, randomness is crucial over here. This is one of the things that distinguishes these interactive proofs from non-interactive proofs. So actually, even in the non-interactive setting, the randomness can be useful in proofs, right? But this is some kind of intermediate between these kinds of mathematical proofs and these interactive proofs, and that's a very nice example of this. So let me show you. It doesn't have much to do with interactive proofs and things we are going to be talking about later, but it's really nice. So let me tell you about this proof system. Okay, so what we are going to do is we are going to look at a non-interactive proof of some statement where the proof being randomized is going to be of some benefit. Okay, and the statement we are going to prove is a statement about matrix multiplication. All right, and a statement is going to be that there are three matrices A, B, and C, and the statement is going to be that C equals A times B. I'm thinking about what would be the best way to write this. Okay, so I want a proof that C is equal to A times B, or rather, let me not even think of it as a proof, right? I want to verify. And I am given, let's say I am given three matrices in, and let's say for the moment that, and pretty much for most of today, let's say we are working with arithmetic over F2, okay, arithmetic modulo 2. So we're going to be, people are familiar with that, right? I expect you have encountered this in the past few days as well. So we're always going to be working with, I'm going to write it as F2, this is just bit 0 and 1. So I'm going to be working, let's say I give you three matrices C, A and B that are n by n square matrices, right? And you want to verify, let's say for yourself, you want to verify that C is equal to A times B. So how can you do that? What is the complexity of doing this? What is the most efficient way of doing this? Or how can you do it at all? What would be one example of? Yeah, that's one simple thing you can do, right? You can do the computation yourself because it's not an expensive computation. You can do this in, so one approach is to compute A times B. Let me give it a name so that I can use it later. Let's say I compute this matrix D that actually is A times B, and you check whether this is equal. This is one approach to doing it. And this takes, just 1 second, this takes whatever time it takes for matrix multiplication, right? Which is this n to the omega, where this omega people keep improving over time. Right? You had a question there?
We can take a random vector and multiply it with C and multiply with AB and then check if there's.
Yeah, so this is what I want to point out. So this is one way of doing it, where you actually compute it and and it takes n to the omega time, matrix multiplication time, and you verify this, right? There is a faster way of doing this that uses randomness, okay, and that really relies on the linearity properties over here. So what we are going to do, and this is called, I may not be spelling this right, but this is called Frival's algorithm. Right, and what you do here is you take advantage of the fact that these matrices are not just arbitrary objects, they are actually linear transformations, and linear transformations have some very nice properties. The linear spaces have very useful properties. So what you can do is, and this is the entire algorithm. Okay, so you first you sample a random vector in the space you're working with. Sample, let's say some vector v, that is a uniformly random vector in f2 of length n, and what I'm going to do is check whether the this v, I want to think of these two as linear transformations, and I want to verify that they're the same linear transformation. That's what I want to do, right? So I'm going to check that if I apply this transformation to v, I get c times v. I want to check that this is equal to a times b times v. Okay. Now, before anything else, what is the complexity of this? What's the running time of n squared, right? Because the way you can do it is you multiply this with b, that's n squared, and then you'll get another vector, you multiply with 3 is n squared, then this is also n squared. So this is already faster than the previous thing we were doing, right? And where does it work? So again, what does it mean to work? By work, we again want to ask for the two properties we ask for general proofs. We want completeness and soundness, right? We want that here completeness means that if C is in fact equal to A times B, then your check should pass, and if C is not equal to A times B, it should not pass, right? So completeness is obvious, right? If C is in fact equal to A times B, then this will be equal. So that's not something you really have to worry about. So what we really need to talk about is the soundness. So what happens? How can you argue? Like what is the how can you think about the soundness of this procedure? If C, let's say C is not equal to A times B, how can you talk about the probability that the check passes? Mm-hmm. Mm-hmm. This is true, and this is one thing to I think to highlight actually. The one important thing about this procedure is that it is not perfect, right? Because even if C is not equal to A times B, there is some probability. The probability that this check will pass is non-zero. If V happens to be a zero vector, which happens with probability 1 over 2 to the n, then this will pass for any C and any A and B, right? But what we want to hope for is that this probability is not too high. That the probability that the check, if C is not equal to A times B, what you would like is that the probability that this check passes is not too large. If it is equal to A times B, it passes with probability 1, and if it is not, then you want it to pass with small probability, which you can then amplify by doing, again, repeating this many times with many independent V's. And so how do we talk about this? How do we argue about what is the probability that this happens? Actually, there could be other cases. For example, let's say that for example, let me show you some example here. So let's say I take I don't want to actually write out matrices. Let's say, okay, the thing to think about here, I want to write this slightly differently. So the C, this condition is the same as saying that C minus A times B times V is equal to 0, right? 0 to the n. This is what I'm checking for. This is my condition, and now what are the values of V for which this can happen? If V is all 0, this can happen. Can there be other values of V for which this can happen?
We can fix all but one element in the V. So for only one choice of that element, it will be 0, and for all the other choices, it will not be 0. So if the range is more than 2, so it will be at most half.
Could you say this again? Can you say a bit more?
All the elements of V part 1.
So V is some long vector, and you are fixing like many of the elements, but one of them you are not fixing. Okay.
Like there will be many possibilities for that element, but for only one, it will be 0.
Okay. That's actually a very good way of thinking about this. One thing I should point out before we proceed with this is we are only working with F2, so it's just 0 and 1. But yeah, this is sort of how I want to go about it, right? So think about this C minus A times B, right? It's going to look like it's going to be some matrix. And what do you know about this matrix? Mhm.
Whichever non-zero vectors which are mapping to the zero can collect at kernels or null space. So those will be some non-zero vectors which will be mapping to zero again.
Yes, so this is an answer to my earlier question that there could be more vectors than just the all zero vector that could map this to zero, because if this matrix happens to be full rank, then there won't be any other vectors. But if it is not a full rank matrix, then there will be some vectors in its kernel, right? There will be an entire linear space in its kernel, and any of those vectors could be mapping this to zero. And what do we know about this C minus A times B? That's the only thing we know, right? We know that it is not zero because we're talking about soundness. So we're thinking of the case where C is not equal to A times B. So the only thing you know about this matrix is it is not zero. Apart from that, it could be some arbitrary matrix, and you want your procedure to work for any such matrix. So for any non-zero matrix, you want to be able to say something, right? In fact, its kernel could be very large. But what can you say about the kernel of any non-zero matrix? How large can the kernel be? Right. So we know that the 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 by this rank nullity theorem that you were talking about, that the size of the kernel of this A, so it's going to be a linear subspace of some rank, right? We know that this is equal to, in fact, this is equal to, because it's like a field of size 2, this will be like 2 power n minus the rank of A of any matrix, right? This is basically the rank nullity theorem, and so this should tell you that if the rank of A, and note that this matrix is not 0, right? That means its rank is at least 1. So this means that the size of the kernel of C minus A times B is at most 2 to the n minus 1. Oh, the 2 is there because we are working with in a field F2. So the rank of so you can think of it as like the size of a linear space over a field of dimension some d is basically the size of the field power d, because you can take all possible. Imagine taking a basis and taking all possible linear combinations, right? So you can think of it that way. But I'll get to a simpler way of thinking about this. But just because we started talking about this, we can think of it also in this way, where you can bound the size of the kernel of this matrix, and then if you take a random vector, what is the probability it will lie in the kernel? Because if it lies in the kernel, you will make a mistake and accept, right? So the probability it lies in the kernel is at most this divided by 2 to the n. There are 2 to the n possible vectors, out of which these many are bad. So the probability you'll get a bad vector is, so the probability that your vector v lies in the kernel of C minus A times B is at most 2 to the n minus 1 by 2 to the n, which is equal to a half. So you can bound the probability that you would accept if C minus AB is not 0. If it is 0, you'll accept with probability 1. If it is not 0, you'll accept with probability at most a half. Right? But that's a simpler way of thinking about this. Let's even not think about it this way, right? Because we don't need anything as sophisticated as this to talk about it. Instead, we can think about it the way someone here was saying, right? What you can do is you can show that for any vector that satisfies this condition, there is at least one other vector that does not satisfy this condition. Right? How do you do that? I want to show if there is a V that satisfies this, then there is some U that does not, there's at least one U that does not satisfy this. Yeah, so what you can do, I'm not going to work through this fully, but I'll tell you what the idea is. It's not hard to work through. So you know the C minus AB is not 0, not all 0, right? That means there must be some column here that is not 0. That's not all 0. That has at least 1 somewhere. Right? Now suppose we have a vector V such that this times V is 0. Right? If I flip the bit corresponding to this, let's say this is the bit that gets multiplied with this. This may be a 0 or 1, I don't know. But if I flip that bit, that gives me, so I start with this V, that's like this. And instead, let's say it starts with a 0. But instead of this, let's say I consider the same setting everywhere else. but this bit I change. Right? Now the product of C minus AB, so this is some V, this was V, this was some V prime. Now C minus AB times V prime is just C minus AB times V plus this column. Right? So this is some column. Let's say this is just the I'll refer to this column. The value of this column is U. This is some column U. Okay. Now C minus AB times V prime is C minus AB times V plus U, and this is 0. So this is equal to U, and you know U is not 0 because that's how you chose U, right? And by doing this, I have taken every vector V that satisfies this property, and I have changed it to another vector that does not satisfy this property. So for every vector, and also you can verify that this is also injective. Actually, it won't be injective. Well, you can do some things. You have to be a bit more careful than what I'm just saying, but this is basically a proof that for every vector that does map this to 0, there will be at least one other vector that is not mapping it to 0. And you can get an injective map with this property, meaning that the number of vectors that do not satisfy this property is at least as large as the number of vectors that do satisfy this property. And that will give you exactly the same argument statement again. And the probability that you will find a bad vector is at most a half, because there are at least as many good vectors as there are bad vectors. Right? Is it okay? Any questions about that? Yeah, you can get it from that. But you don't even have to think about that. You don't even have to know what a kernel is or anything to see that this works. And then you can amplify this again by picking many independent random vectors and seeing what happens. Right, and this is an example of how randomness can help even in the non-interactive case, where it's giving you some improvement. It's letting you do something better at the cost of having some error. Right? Because here, even if you repeat, there will be some small probability that you just pick bad vectors every single time. So that you cannot really avoid. But you can make it very small. You can make the error probability very small. And in fact, the only cases where you can actually avoid this error are basically the whatever statements already have these kinds of non-interactive proofs, all that have these mathematical proofs, which corresponds to, I don't know how many of you are familiar with complexity theory. How many of you have taken classes in complexity theory? Yeah. Okay, so I'll not spend too much time on this, but you can basically show that the only kinds of problems, the only kinds of statements that have interactive proofs with that have interactive proofs with no soundness error, basically with no error in this kind, no error of this type, are the problems that are in NP. So I'm not going to spend too much time defining this. So if you don't know what these things are, don't worry about it. It's not a big deal. But I'll just say this for all those who know that so interactive proofs with no soundness error. But soundness error, I basically mean this, that 1/3 over that is what I refer to as the soundness error, because it's the error in the soundness property, right? So interactive proofs with no soundness error, meaning the soundness error is 0, you only have for languages in this complexity class called NP, which basically corresponds to problems that already have these kinds of mathematical proofs, that already have these kind of non-interactive proofs. And more generally, even more general, the class of languages that have, the set of languages that have these kinds of interactive proofs, even more generally, we also have some understanding of that in terms of some of these complexity theory classes, right? And this is, I'm going to write this down and then I'm going to explain this. So this is a theorem that was proven back in the early 90s, and it was quite a significant achievement at the time. So one thing that we know, one natural question that we can ask here, right? I've shown you some examples where interactive proofs with this randomness and all is giving you something, is giving you some advantage over non-interactive proofs, right? Over non-interactive proofs that have no randomness. There's some advantage here, and you can ask how much of an advantage is it? Like, what can you do with these interactive proofs that you could not do with these? Like, how much can you do with these kinds of interactive proofs? What kinds of problems, the way we were talking about it, what kinds of problems, promise problems, have these interactive proofs? Do all promise problems have interactive proofs? Does anything that you define does not have an interactive proof? And the answer to that is seems to be no. Answer is no. You can actually prove that it is no. There are languages that problems that do not have interactive proofs, and you can say even more. You can show that the set of languages, the set of problems. Like if you can show the following statement: if a problem has an interactive proof, the way we have defined it, then that problem also has an algorithm that runs in polynomial amount of space. That's what the right hand side of what I wrote down means. This P space stands for polynomial space, and what this is saying, what one side of this equation is equality is saying is, if you have an interactive proof for some problem, then you can show, it's not that hard to show. I'm not going to do it today, but you can show that there is also an algorithm for that problem that you can in fact extract out of this interactive proof. There's an algorithm for the problem that runs in a polynomial, that uses only a polynomial amount of space. You had a question? Somebody have a question? Yes, I can tell you. I can tell you a little bit. I'm not going to go into too much detail, but I can tell you roughly what you do. So the idea is that so you have this. What you want to show here, I have not placed in our modeling of interactive proofs. We said the verifier is polynomial time and the prover is computationally unbounded, right? You're not placing any sorts of bounds on the resources it has. But what you can actually show is that you can take any interactive proof which has some arbitrary prover, and you can convert it into another interactive proof while the prover only uses a polynomial amount of space. Right? But you see that is sufficient, right? If you can do that, then it's sufficient because the verifier only uses a polynomial amount of space. If you also knew that the prover only uses a polynomial amount of space, then using just a polynomial amount of space, you can simulate both of them and run both of them yourself. So it will be sufficient to show that. Right? Now, how do you show that? How do because the prover is some arbitrary thing, you don't have no idea what it's doing. How can I show that you can implement it in polynomial amount of space? Well, the important observation here is that it doesn't so much matter what the prover's algorithm is doing inside its own head. All that really matters is how it responds to various messages. Right? You just need to know if the prover sees this message, this is how it will respond. If it sees this message, this is how it will respond. That's all you need to really know. And you can take advantage of this, and you can show that this you can actually do in polynomial space. That any prover strategy, any prover algorithm you have, you can change it to be in such a way that it only uses a polynomial amount of space, and that's the key to showing it. It's not that hard to do, but actually, yeah, if you're interested, you look at my website. There should be references there to proofs of this, right? But that's the high level approach. That's how you come up with the algorithm. But the algorithm, it's not going to be a nice algorithm. It's going to do some exponential time. It's not going to be polynomial time. It's going to be some exponential time, maybe, probably. Right?
Exponential only because of the going through the random choices deterministic.
Something like that. Yeah. It's going to sort of try to figure out, okay, what response can I give that will make the verifier accept with highest probability. That's what it's sort of going to do. Like your strategy is going to be, you see a message from here, and then you think, okay, what response if I give will make the verifier accept with the highest probability, and then you give that response. And to figure that out, you need to look through all possible ways the verifier can respond after this. So you do something like that, and you can do this. Yeah. So the other direction. So what I have said so far is that if any problem has an interactive proof, then it has a polynomial space algorithm. Right? And that's the easier direction to show. The proof is essentially what I was just describing. You have to work it through. But the other direction is also happens to be true, where you can show that if a language has a polynomial space algorithm, then from that algorithm we know how to construct an interactive proof system for that problem. Right? And this is much harder to do. This took a lot of time. This is the direction that took a lot more time to prove. And it involves some very clever, very interesting protocols, very interesting proof systems that unfortunately I don't have time to go into today. There's some very nice things there going on there. It took people a few years to prove that, what can I say about that? It involves ideas that are not, that it's not obvious that they are relevant to this. It goes through certain algebraic properties of polynomials and all that. It's very interesting. Again, if you're interested in this, you can look for, there'll be some references from my website. But also, the theorem is important enough that if you take any complexity theory textbook, they will have a proof of this. Like if you take like Aurora Barak, for example, it's a pretty good complexity theory textbook, they'll have a proof of this statement. It's very interesting. I recommend looking at it if you're interested. But this is basically how powerful these proofs are. They can prove that you can construct these proof systems for any problem that has like a polynomial space algorithm. Whereas these NP is much more restricted than this. The set of problems that have these non-interactive deterministic proofs is much smaller than, as far as we can tell. These things we can't really prove so far because our techniques that we have are not really up to it. But because we believe that this is much less powerful than interactive proofs in general. All right. Did I want to say anything else? Yeah, this is what I wanted to say about the power of these things, right? And yeah, so interaction is important, randomness is important, and these errors give you these things. Okay, so now we have talked about the basics of interactive proofs. We talked about the definitions. We saw some examples, and from here I would like to move a bit more towards. And from here there are many directions you can go. You can ask about, for example, you can ask more fine-grained questions about these proof systems. For example, you can ask, okay, what if I have, we have compared the proofs we had to proofs that are non-interactive, which means they have only just one message in the entire interaction that goes from the prover to the verifier, right? But you can ask, okay, what if I had two messages? What if I had three messages? I restrict my proof system. I can restrict my proof system in various ways, and I can ask, what is the power of that? What if the interaction is only allowed to have these two messages, like one from the verifier to prover, one back? And people have looked into all of these questions, and there are some very interesting results that have come out of this, very interesting protocols that have come out of this as well. But the direction I want to take is more towards what we'll be talking about for the rest of the day as well, which is more towards some more cryptographic perspectives on these interactive proofs. Okay. And I want to start by pointing out some other properties that the protocols we discussed already have. All right. Let's start with this protocol itself. So, a property here that I want to point out is that, so what's happening here? There's these two graphs, and the verifier wants to know whether they are isomorphic or not, and the prover is able to prove to the verifier that they are not isomorphic, right? But it's able to do so. But I want to point out that at the end of this proof, the verifier is no better off than it was at the beginning of the proof in terms of its own ability to tell whether graphs are isomorphic or not. Right? Like one way for the prover to have proven this to the verifier, if it had been possible, would have been to teach the verifier how to distinguish between graphs that are isomorphic and graphs that are not isomorphic. Right? If the prover had some algorithm for that, it could tell the verifier, here's an algorithm, and then the verifier can run the algorithm efficiently and figure it out. Right? But that is very different from what's happening here. Right? So here, at the end of the protocol, if now you are some other person, okay, that's the verifier, and the verifier, let's say, interacts with the prover a lot during the course of this thing, and now let's say the prover goes away somewhere, and there's just the verifier. Now you come into the place and you look at these two graphs, and let's say you ask the verifier, okay, prove to me that these two are not isomorphic. The verifier turns to you and says, see, I talked to this prover and I'm now convinced that these two graphs are isomorphic, right? But you don't trust the verifier necessarily, so you ask the prover, okay, can you prove to me that the two graphs are isomorphic or not isomorphic, right? And in this case, with this protocol, there is no way for the verifier to do that. Right? And you can even think of it in the example we talked about earlier with the coffee and the tea and everything, right? Where I proved to you that these two are different drinks, but I have not taught you anything about how to distinguish between them. Right? If you could not distinguish between them before, you still cannot distinguish between them, right? And this property of a protocol where you don't learn anything in the course of the protocol is called zero knowledge, right? Because you are not gaining any knowledge in the course of the protocol, right? And this is what I want to talk about for most of the rest of the day, right? Starting with thinking about how to talking about how to even talk about it, right? How do you even formalize a property like this? Like how do you even say I have set up the model the way, okay, I'm not going to change the model anymore. There's the prover and the verifier. The prover is inefficient, prover is unbounded, verifier is efficient, and I'm going to keep the completeness and soundness properties the same, and I'm going to specialize my definition a bit more. I'm going to ask for an additional property of a proof system. Yeah. Oh, I just mean polynomial time. Yeah, I always mean polynomial time when you say efficient. Which is always an NP? No, it did not be, because there is no necessarily there is no like an NP proof. For it to be an NP, you need to have a non-interactive proof, but you don't really have that, right? Yeah. So verifier is polynomial time, prover is computationally unbounded. I'm not going to change that. I'm still going to ask for completeness and soundness, but now I want to think about how I can ask for this property. So there is something here, right? Like there is intuitively there is some additional property this protocol has that I just described. That like I described like an example of an implication of the property, where if a third party comes and asks the verifier to prove that the graphs are not isomorphic, it cannot do that. Even if it interacts with the prover 100 times, it does not have the ability to do that. Right? That's an observation about this protocol. Right? Now, and what I want to do is I want to isolate this property. I want to ask about, okay, what can this property look like for other protocols, or how can I formalize this property? How can I think about this property? And the way I would like to think about it, at least in intuitive terms, in natural language terms, what I would like to extract out of this, what I would like to see in a protocol is, I would like to see the property that in the course of the protocol, in the course of engaging in the protocol, the verifier does not learn anything new, right? So how can I say this? How can I capture this property in any sort of formal sense, in any sort of rigorous sense?
Same as you said, the third person who sees this interaction knows as much about proving this non-isomorphism as the verifier.
So how would we think about? So you want to say that as a third person knows as much about proving this. Yeah, that is the sort of thing we want to say. But can you think of how we can state it? How we can write down a definition of this property? How we can isolate this? How we can model it? Or what does that mean?
If you don't trust the random, like if the random oracle is like randomness is replaced by some deterministic function, then your faith on the proof is zero, or like the probability the proof works is zero.
So the randomness is replaced by a deterministic function. Say again.
The entire transcript was written down and someone else is looking at it. The faith in the proof was zero.
This is the sort of thing you want to say. You want to say that because what does this is one of the things you want to be implied. Whatever we come up with, you need this to be implied. You need to be able to say that if somebody, because one thing the verifier can do is it can write down whatever it sees, right? It can say, so you go to the verifier and you say, okay, so the verifier has been you go to this verifier, right? And the verifier tells you, see, these two graphs are not isomorphic. And you ask the verifier, okay, what is the proof? Prove to me that it's not isomorphic, right? One thing the verifier could do is, imagine it has spoken to a prover earlier, right? It can record all of the conversations it has had with the prover, meaning it can record the value of the B and the R and the B prime, and the H is implied by the R, so you don't have to talk about it separately. So it can record these values and it can show you, right? It can say, okay, I talked to this prover, there was this prover, I talked to it like 100 times, and the first time I had this value of b, this value of r, and the prover gave me this value of b prime. Second time I had this value of b, this value of r, then I had this value of b prime. So it can give you like 100 values like this, right? This is something it can do. And what we would like to say is that even this is not a valid proof. It's not a sufficient proof. Because we don't want the verifier to gain anything out of this interaction. And one of the things it could gain is the ability to convince a third party, right? And we don't want it to gain that. So in particular, you want to make sure that if the verifier does this, and if the verifier writes down, it records all of its interactions with some prover and claims this is what I saw, you don't want this to mean anything. Like you don't want this to be a convincing proof. Pretty much like what you said. You don't want this to be convincing, right? And it turns out that this approach is actually thinking of it this way actually leads us to a pretty good definition that has all sorts of other nice properties. So let me try to formalize the property in this manner. So I still want the completeness and soundness. I'm going to erase this and write something here. Okay. So now what is the simplest way in which you can make these recordings, I'll refer to these as transcripts, okay? Or what is the simplest way in which you can make them unreliable as a proof? So the verifier says, okay, here I had these conversations with the prover, and you want it to be not valid as a proof. You want it to be something that you cannot really trust as a proof. So one way of arranging for this to happen, one situation where this would possibly happen, where you can disregard this as a proof, is a situation where the verifier might itself have come up with these transcripts, right? Because if it is possible for the verifier, because the verifier is efficient, right? If it is possible for the verifier itself to have come up with these records of because what is the record? The record is basically there is some b or b prime. Let's say the verifier says, okay, here's the first conversation I had with the prover. Then it says, this is the second conversation I had with the prover. P2 prime, and so on. It gives you like 100 of these, right? But if it was possible for you to say, okay, if you can tell the verifier, okay, you are showing me all these transcripts, but it's possible for you to come up with this on your own. In fact, even I can come up with it on my own. So how can I take this seriously as proof? If that was possible, it seems a bit contradictory, right? Because the verifier, to get these things, you have to interact with the prover. But if it was possible for the verifier to do that, then this would not be valid as a proof. Right? Because if anybody can come up with this without even knowing whether the graphs are isomorphic or not, then it doesn't make sense. Then it doesn't. Then you don't care that, because you could have come up with it on your own, right? So, so is that the case here? If you look at because the verifier is going to say, the verifier says, okay, this is these two are not isomorphic, and here are my transcripts. Here is what my conversation with the prover. Now, could the verifier have come up with it on its own? So the prover does have exponential power, but somebody who's trying to come up with this may have some other things that the prover cannot do. Any ideas? Is there some way? What I'm asking is there some way you can see where you can actually come up with these things on your own efficiently?
First one, you can just randomly tolerate,
Mhm.
and then you can do a relabeling and then set b prime to be b1.
So this I could do, right? Let's say again, let's go back to the scenario we were in earlier. Where let's say, imagine I am the verifier, right? And imagine I want to, like, for some reason I want to lie to you. Like, I have these two graphs. I have never talked to a prover in the past, right? but you come up to me and I want you to believe that they are not isomorphic, right? In that case, I can come up with this on my own, right? Because I can say, I can pick this B1 at random, I can pick the R1 at random, and I can set my B1 prime to be equal to B1. Right? If I had talked to the actual prover and the graphs had in fact not been isomorphic, this is exactly what I would say, right? Because of the perfect completeness property we have. If the graphs are not isomorphic and I actually talk to an inefficient prover, then that's what I would see. I would see a random B, a random R, and a B prime that is equal to the B, because I will always accept, right? But this I can make up on my own as well, without even talking to the prover. I can make this up. Like if I want you to believe that the graphs are not isomorphic, I can do this. I can say, okay, here's what I saw from the prover, and I can make this up completely on my own, right? And because I can make this up on my own, you should not trust this as a proof. Because if all you see is this list of supposed interactions with the prover, you should not trust this, because I could have come up with this on my own very easily, right? And this is what you want to capture, right? This is, and so I don't. So this approach of me trying to prove to you that the graphs are not isomorphic cannot work, because you won't trust this, because I could have come up with this on my own, right? And this is the approach we are going to take to defining this property we want. We are going to say that an interactive proof is zero knowledge if you can do this. If for any instance that is in the language, any S instance, in this case any pair of graphs that are not isomorphic, you can come up with, you can simulate, that's the term we would use, you can simulate the interaction with the prover on its own, right? So I'm going to write down the definition and then we're going to talk a bit more about this. So what I'm going to say is, I'll write it here. I want to say that there is some algorithm that can generate these things, right? And I'm going to refer to that algorithm as a simulator. Okay, so I'm going to say there is some efficient, we don't say poly of n, there is some polynomial time algorithm called the simulator, such that for any instance that is in the language. So I'm always talking about this pi, right? This is y and n. For any instance, any S instance, I want to say that the simulator, when given the x, it outputs something. It's going to be a randomized algorithm. Okay, it's going to be a randomized algorithm because the randomness is inherently in the protocol. So you can't simulate it without randomness. You can't generate transcripts without randomness because there is inherently randomness in the protocol. So it's some randomized algorithm. So if you run it with this input, it will produce some output, and that output will follow some distribution, right? And what I'm going to ask is that the distribution that comes out of the simulator when given this input x is the same as the distribution that comes out of the that is a distribution that the verifier in this thing sees. It's basically the distribution of these transcripts that the verifier sees. Okay, and I'm going to write this. I'm going to introduce a new notation here. I'm going to call this the view of the verifier. So the view of the verifier when interacting with the prover on input x. Right, it's the view of the verifier when interacting with the prover, and the view consists of. So let me define that here. So the view of the verifier when interacting with the prover on input x, it consists of two things. It consists of the verifier's randomness, like whatever private randomness it uses. In this case, for example, it sampled this B, but it never sent the B, right? But the B is still there. The verifier knows the B. So it's going to be whatever the B verifier sees, which includes the random choices it makes, the random strings that it uses to make it run its algorithm, and all the messages. So this view is going to be a distribution that corresponds to the joint distribution between these two. So if you think of the entire protocol, right? If you think of all of these as random variables, think of all of these as random variables, they follow some joint distribution. Because they're all correlated, they're not independent, so they have some joint distribution. And the view on this is exactly that joint distribution. It consists of the verifier's private randomness and all the messages exchanged during the protocol. And it does not include the proof. If the prover uses some private randomness, it does not include that. It's only what the verifier sees in the course of the entire protocol. Yes, so we'll get to that later. So for now, let's talk about these being perfectly being the same. In general, you would want to relax this, and we'll do that a bit later. In fact, this definition is a bit strong. We'll talk about that more later. So I actually want to ask, for now I want to ask, they're perfectly the same. And I want to claim that this you can actually get for this protocol. So let's talk about two things before we go for lunch. Let's talk about why this protocol meets this definition, and let's also talk a little bit about how to interpret this definition beyond what we just talked about, right? So first, I claim that this protocol meets this definition. So why does it meet the definition? How does it meet the definition? So I want to, and to show that, you need to show a simulator. You need to be able to show me an efficient simulator that can simulate the view of the verifier, right? In this case, what is the view of the verifier? It's basically what I said, what I was saying earlier. It's there's B, the R, there's the H, but H is determined completely by the B and the R, so you don't have to think about it separately. It's just implied by these things. And there's the B prime, right? That's the entire view of the verifier. And so basically this, right? This is what the view of the verifier looks like in the protocol. And you want to come up with a simulator that can simulate this view, that is efficient, that runs in polynomial time. And it doesn't have access to the prover, right? It runs entirely on its own and can come up with the same thing. So what is that simulator? Exactly, right? So the simulator for this is exactly what we just talked about. You just, let me write it down. So the simulator, it gets G0, G1, which is the instance in our case, and then it's going to pretty much run the verifier's algorithm and just fabricate the prover's message. So it's going to sample this 0, 1, and it's going to sample like a random relabeling, and it's just going to output B R and just B again. Instead of B prime, it's B, right? And as we said, if the instance is a yes instance, because that's what you want to really protect the prover in, then this is exactly what the distribution of what the actual view looks like, right? So it meets this definition. So is that clear? Any questions about this part? Because we're going to be talking about some more detailed things like this after lunch. So I want to make sure this part is clear so far. Is the definition clear? And is it clear why the output of the simulator matches the view of the protocol? Okay, great. Yeah. So this shows that this protocol also has this property, right? And among other things, like we were saying, this property implies it implies the statement we were talking about earlier, that now it is not possible for the verifier to use what it saw during the protocol as a proof. Right? It cannot say, this is what I saw when I interacted with the prover, please believe that the graphs are not isomorphic. It cannot say that because it could have plausibly come up with those things on its own efficiently, right? So then what is the worth of that statement, right? And we can even think about this more generally, like it's not just that the verifier cannot show the transcript itself and say this and claim it to be a proof. It can't derive anything from it as well. Like it sees these 100 transcripts. It's not like it can put them together in some intelligent way to come up with a proof that a third party should believe, because it can generate all the 100 transcripts on its own, right? So whatever you can derive from this, you could have generated yourself. And because the transcripts are the same distribution as the actual view of the prover, it cannot derive anything from its actual view and present that as evidence, and present that as a proof that the statement is true. Right? So in this sense, in this specific sense, it's not learning anything in the interaction with the prover. Because anything that it could possibly have learned from the interaction, it could have generated on its own. Right? It could be learning things that are not obvious by interacting with the prover. It's just that whatever it learns, it could have generated on its own. That's the thing. It's not so apparent in this protocol that it may learn non-trivial things, because here is just one bit, right? And it already knows that bit. So it could be learning some non-trivial things. It's just that whatever it learns, it could have figured out on its own. That's what the simulation condition says. So far, we haven't talked about that yet. So far, we've only talked about verifiers that follow the protocol as it is written. But of course, in reality, we'll have some other considerations as well. But we'll get to that after lunch. So it's 12:30 now. Let's break for lunch now, and we'll continue at 1:30. Right? I think it's 1:30.